Welcome back, everyone. Hopefully, everybody is having a great time today. I know you are having your assignments. So, you are also having a quiz. I'm going to give you that quiz during the lab time next week, the one that you missed it during the lecture time for Monday. But still, we are going to have at the end of this class the assignments, the problem that you're going to solve. So stay with me. I'm going to quickly explain the timer as I already recorded the lecture for the intro. Hopefully everybody got the chance to go see it. If not, I'm going to quickly show you where it is. You can find it as a part of your midterm. Therefore, go watch that one. Make sure you are not missing it. Today, I don't want to spend too much of time on explanation. It's only timer is left from this part. I'm going to quickly explain it, go over a little bit of the information about the structure of timer and counter inside the microcontroller. Most of the detail, they are already covered during the lab time, but still I'm going to look at the structure, show you all of those things that we did during the programming inside the lab, how they are working in terms of hardware. In there, you do not have option to look at inside the microcontroller, but still I do have the diagram. So I'm going to quickly review that one. If the time is still allowing us, then I'm going to look at two problems for you. And then we'll stop it right in there and we'll start the assignment. So just all I want you, just have a fully charged device. You do not need it for writing. I already printed out the exam. They are here. You just need to write them down, take a picture. If you have even your cell phone, that's good enough to upload it to Avenue, and then you are good to go. So let's start with kids. Do not be really stressed for whatever is going on about the exam. It's not even an exam, it's just one problem, and I solved the exact same one for you before during the class time. And of course you have the recording, you have the solved problem, all of them are there. So do not really be worried about that. So I've already covered all of this slides, and I've left that previous recording right in here. So, so what I'm going to cover today, as I mentioned, is going to be about timer and its importance, more specifically in embedded system application. Why we need it? Any idea? Why timer and counter are really important in embedded system application? In fact, in microcontroller, timer and counter, they are going to be the hardware part of the microcontroller. As I mentioned earlier, you are not really seeing them. Most of the time they are included, but there are situations in some microcontroller, those are some external pieces that you may register. But the importance is coming because in real world, most of the things we deal with is digital, right? Everything around us is digital. Therefore, none of the things that we are seeing around sensors, maybe in real world, they are something understandable for the microcontroller. In the other hand, kids, microcontroller doesn't have any understanding, or I would say any sense of time. That's why we need a procedure to convert all of those signals. And that's exactly the time that in addition to those procedures, we need to sync the speed of those signals with this, like the speed of the processor. Therefore, we need to sometimes delay. And of course, we need to make the microcontroller to somehow understand the time, how many time and how long. That's why this is super important in embedded system application. I'm going to just somehow summarize this one for you. As I mentioned, microcontroller by itself doesn't have a sense of time. Let me bring some example. Suppose there is a timer in the traffic light. Everybody noticed that. There is a timer in traffic light. Sometimes that timer, which is changing the color, right? And sometimes at the end of all those colors, it's still a little bit of time for people to just understand it and maybe pass the junction and everything. So all of those, you need to know the time is in frequency format. Time by itself, as I said, doesn't have any meaning for the microcontroller. It's in frequency. Therefore, we need to convert it. We need the inverter. Frequency is supposed to become the inverter of time. So all of them are in terms of frequency. Therefore, we need a timer to capture them. So another thing is for motor design acceleration. We need to look at the velocity, and you know that the velocity is changing by the change of time. Even that velocity is something which is in the format of frequency, right? Any engineer who's focusing on the motor design, they have to, for example, if they want it to become a fast or maybe a slower motor design, they have to play around with the frequency. And then frequency will be converted to time to become understandable. Another thing is we need time delay. Time delay, for example, I'm using this pen to write into the computer. The speed of this is not the same speed as the computer. We need a time delay to sync these two together. When I write, it might be slower or faster. It depends which kind of devices that you are using. Therefore, that's a delay. Again, it is a counter, right? That delay will help to sync the speed right in here. That's why we need to have timer and counter in embedded system. I would say it's one of the major components in embedded system, right? So knowing that, you may want to understand how many timers do we have. In fact, we do have two timer structure. One of them is output compare. The other one is input capture. Output compare, I would say, is familiar with you. Why is that? Because last semester teaching you mechatronics, remember, you had very similar robot in there. To program it also in there, the language we were using PLC. We were not using C or actually, we were not using even microcontroller. It was PLC. PLC is a completely different programming, but the basic or structure of our understanding from what we do is gonna stay the same. Even in PLC programming, we had timer module, we had counter module, and we had to look at those in order to just program the robot in a way that it can grab some component. In this picture, for example, I'm having a steel conveyor and I'm having a robot. Very similar to what we had last semester. So this robot's supposed to grab those blue components, hold them for some time, suppose for 5 seconds, and then since the conveyor is moving, there should be some delay in order to drop them. Of course, we need to apply some delay in here. In the other hand, we want some space between the components, right? We don't want them to stick to each other. Therefore, robot is just grabbing the components, bringing it up, probably in some situations, since it has to move them from one location to another location, we have to give it another delay in order to move from one location to another location. And then we have to also change the angle, and all of this takes time. That's why we don't want this whole thing to happen super fast and mess up with the event. And then we wanted to drop it in a different location with some space between the components. Therefore, one of the most important application of timer and counter, more specifically in automation. Automation could be in any industry, automotive like industry or any other industry, is going to be the timer and counter. Now, looking at here, when we say output compare, means the focus is on the output event. The output event for this robot and conveyor is moving those objects. Therefore, the microcontroller is considering a preset value, and that preset value is that time. For example, for 5 seconds. In every 5 seconds, grab one component, change the angle of rotation, and then drop it in a different location. That's what we call it a preset value. Any system or any timer terminology which is focused on the preset value for the timer or counter, that's what we call it output compat. And any time that the timer is done timing, it will generate, based on the way that we program it, it will generate a 0 or 1. So that's the basic of output compat. Means the very last event will be compared with the preset, and the next event is set accordingly, right? It will be set to 0 and 1 based on the preset value for the entire event. Now, this may happen over and over and over. Suppose you are going to repeat maybe 1,000 times. If you are going to pick some object, bring them up, count for maybe 5 seconds, as I said, and then drop the same item, maybe in a different location, and have maybe some space between those, then probably you need maybe 1,000 times to process this event. And then it takes, like, if you have 5 seconds, then it takes almost 2 hours. It takes almost 2 hours to move all of them. Simply means the timer will stop, the robot will stop at around 120 minutes. And then after that 120 minutes, it will switch off. It will go to 0. It will reset to the beginning. Make sense? But in situation that we are looking at the capture, input capture means now the focus is not on output, the focus is on the input signal. That input signal could be anything. Now we are going to preset the event happening based on the signal which we are receiving. Simply means each time we are reaching to this point is the arrival. I'm going to call it arrival. And I'm having in this picture right in here 2 periods. Maybe, for example, this is 1 period and this is another period. I call them T1 and T2. The very base point of it is this 2. This is one arrival for T1. This is another arrival for T2, right? It will start in there. And then any time which takes for each of this to finish, that's what we call it how long, or the period. I'm going to show it with maybe T, and T means how long it will take, right? Next, for example, it is capturing the time between the 2 rise. This is 1 rise, this is 1 rise, and capturing the time between 2 rise is going to be input capture. How long it will take from 1 rise to another rise, or 1 arrival to another arrival. That's what we call it input capture. Make sense? Next, I'm going to be a little bit quick for today to make sure that you're going to get enough time. And remember, one more time, this is before I move from here. Generally, timer is a counter. Timer is a counter. Why is that? Again, everything is based on frequency, and frequency is inverse of time. So how long it will take for example, to count, for example, 5 count. And that's why we say timer is by default a counter. This part is what we already discussed during the lab. And I'm going to look at the structure of, let me quickly review the structure. This is what you are not able to see yet, but I explained to you what is the TCR1, TCR2, and I'm going to just explain it again in here. So this is the main bus clock. Kids, for us, the bus frequency is something at around, what is the bus frequency for us? Bus frequency is the crystal frequency, I said it during the lab, divided by 2. If the frequency for the, this is in here, I'm going to calculate it for you. The bus frequency is the crystal frequency, usually crystal frequency, I'm going to say it with CF, usually it's given based on the manufacturer information. You can go find it in there. Also, we call it oscillator frequency. Crystal frequency or oscillator frequency, both of them are the same thing. We can get it from the data sheet divided by 2. This is a standard. This is an equation. So if we have the bus frequency, we can, or if we have the crystal frequency, either of them, then for example, for us, crystal frequency, remember, is 16 divided by 2. Then the bus frequency of our microcontroller is 8 megahertz. And again, crystal frequency is given by the manufacturer. Now, suppose I'm having that bus clock. Let me maximize this one. And that I'm going to look at this part. And that's 8 megahertz is going to enter from here. This is the beginning of the process. What will happen next? What is the TSCR2? TSCR2 is a prescaler. I'm going to show it with PR. Remember, 3 bits is going to toggle. Those toggling is going to control the time. Means we are going to have the control register to here is only 3 bits of them in order to look at the frequency. This one will capture the frequency. It will send the command to TCNT right in here. And then in here, I'm going to have, for example, if your bus is 8 megahertz, I'm going to have F to be 8. I'm going to calculate it. And then T, I can calculate from this. It's going to be, if I have 8, then I can calculate the T. What is the T? We did it in the lab. T is going to be 100.125. It's fast, isn't it? It's super fast. And in order to control this, because this is really fast, what do we need to do? We have to have the 16-bit TCNT. Therefore, this will come here. And then in here, this is what we call it counter. So this is going to be our counter. We have the time in here. This is super fast. We have to control it through the counter. And this counter is going to be updated based on the latest frequency. And after that, this is the flag. And in here, the counter reach from, for example, 0000. If the counter reach from this to 16 bits, what will happen? This is 16 bits. Then the timer overflow. This flag is overflowing the timer each time. And it will reset and it will start over from 0000 again. So any time that from 000 will go to 16 bit, this will overflow the timer again. And again, it will reset it to 00 to start from the same thing. Make sense? And now that's what I said technically about when we are going to look at the preset value and go through the process. And again, after the timer is done timing, it will reset. And that reset process is happening through this counter schematic. Make sense? Now, next, I already even summarized this one in a little bit, maybe simpler in here, steps. So enable wait flag. These are going with an order. They will never mess up. If one of them is reposition, everything will be actually ruined. And that's not what it is happening inside the microcontroller. These are all what we discussed in the lab. So I left them in there for your reference. And I'm going to go over one example. Let me quickly open OneNote. You may want to take your own note in here. It's not complicated, it's easy. So before that, I'm gonna bring some of the information from the previous slide. For example, I need, in order to solve that one, these are again from the lab time. I need to look at the prescaler. What was the prescaler bits? The bits in here, I think it is this one. This is TS1. I'm gonna take a screenshot from both of them. Then you know what I am talking about. This one is 1. You may right now ask me, do I have similar problems or examples in the exam? And if I do, am I getting access to this information? And my answer is yes. So These two, I'm going to leave them right in here. And of course, in order to program, I need to have access to this table. And these are all from data sheets. No one is expecting you to generate any of this information, right? For example, so if needed, I'll give them to you. So now the problem is asking me, go ahead, provide a C program. All of those C programs that I teach you during the lab time, I do a lot of calculation for them. Very similar to what I'm going to do right in here. So now as an engineer, you are expected to do similar programming. You are expected to provide a program that to count the number of time the free running timer overflow. I just said, what is the overflow? The flag is overflowing, right? That's why I first explained that one. And then I'm expected to display the binary number on port B. In the lab, we usually show it on port H, which is the LEDs. But here I'm expected to show them on port B and show how often the number change. So far, I explained it through a schematic. I explained the procedure. And now I'm going to do it mathematically. How do I treat such a situation mathematically? This is the TS. Remember, I got it from the previous slide. TSCR2, which is the prescaler for register number 2. And I told you the prescaler is changing. And the next one is going to be this one, actually. This is the CR1. One more time, I'm going to double check. I've got the CR1. Yeah, correct. This is CR1 and this is CR2. And this is your TSCR2, TSCR1. These two. And this is the table for it. So from the example in here, it's already given. XTAL means exactly the same crystal frequency. So I'm having the crystal frequency. I summarize it in here. XTAL is given as 4 megahertz, right? And then divided by 2, remember, divided by 2, I have to make it divided by 2 in order to find the main bus frequency. Then main bus frequency will be 2 megahertz. Now I'm going to look at the prescaler. So prescaler, I have to select if it is that one, I have to select. So means all of them are 0. If all of them are 0, prescaler is going to be 1. Therefore, from here, I'm going to say my prescaler is 1. So I'm going to divide this one by 1. Therefore, I'm going to have 2 megahertz for the timer frequency. Right? And then it means the timer actually counter will be updated within the frequency of 2 megahertz. Means this is the frequency for each update. 2 megahertz is the frequency for each update. Now, I have been asked to look at the situation that I do not have a prescaler, and I have been asked to look at the situation that I do have a prescaler of 64. Prescaler of 64 means 110 from the table. Means 110. Now, to show how often the number change, I need to calculate the frequency. Timer frequency is 2 megahertz, right? And then 2 megahertz means what? Means 0.5 microsecond. Since the frequency is, why is that? Because frequency is 1 over t, and if I have one of them, I can calculate the other one. Now, I have to go back to the TCNT. TCNT was the control, right? TCNT is 16 bits. Is 16 bits. I already said it. We already have that one. That's 16 bits. And from that, 16 bits means what? 16 bits means 2 to the power of 16, which is equal to 65, 536. Now, in order to calculate the TC&T, this is this one. TC&T, I have to just have like the number, which is 65,536, and I already calculated the time. And out of this, if you calculate it, it becomes almost 0.03 second, but in microsecond, it becomes 32,768. In second, I'm gonna write down approximate, maybe this one in second. Means what? Means every 0.03 second, port B will be updated. Every port B will be updated. Make sense? Now, what if I have, if I want to have the prescaler 64? That's for the no prescaler. But now if I have 64, for 64 means I have to come back here. In R2, I have to put down 1, 1, 0. Then this will be what I have. Everybody should know this is 0. And what is this in hex? 6, right? This is 6. And if I convert it, it becomes 0x06. Make sense? This is what we know from the lab. So I'm going to put down right in here. Then it means the TSCR2 in here becomes 06. 0x06 means the frequency is 2 megahertz over, it was 64, right? I need the prescaler 64. And then if you calculate this one, it becomes something I'm going to put down right in here. It becomes, again, as I said, 100, maybe, let me first calculate it in hertz. In hertz, it becomes 31. Let me calculate in hertz, and then I'll convert it to time. 250. This will be in hertz because this is frequency. Now I can convert it for you. This is hertz. In time, if you want it, it becomes the same number, 65,536. Then I have to this time say times this one. This is my frequency over 31, 250 hertz. It becomes almost 2 seconds, a little bit more. Now it takes almost around 2 seconds to change or to update or overflow port B. Make sense? If I have prescaler, it takes almost 2 seconds. If I do not have a prescaler, it takes almost 0.03 seconds in order to each time get the port B to be updated. So I have a few more minutes, so I'm gonna quickly, this one I already explained again. I just explained in the previous, this one are all lab, and maybe this example. Let me look at this example for you, and then we are good to move to the next one. This example, example 3, again is crystal is given, crystal frequency is given. This is example 3. Because all of these examples, I already solved them and I already uploaded the solution for you on Avenue. You can find them in there too. For this example, again, I have XT. Now you know what is this, right? It's 4 megahertz, right? And then, again, using the same prescaler, right in here, these two prescaler. Based on those two, I'm gonna first say for prescaler 1, if my prescaler is 1, I have been asked to write a program to generate a square wave with a period of 10 milliseconds on pin 4 of port T. PT4 means pin 4 of port T. So I'm looking at 10 milliseconds. and I'm looking at generating a square wave. So I have to consider again prescaler 1, and then if frequency is 4, I have to divide it by 2, remember? And then my main bus again is 2 megahertz. And this is main bus. Now, I have the main bus, which is 2 megahertz, which is actually for prescaler 1. How about timer frequency? Now I look at the timer frequency. Since I have that one, I can simply calculate. It's 2 megahertz. The timer frequency for that, it becomes again 0.5 microsecond. Now, again, like the other one, TCNT. TCNT is what? Controller. TCNT is the 60, is counter, sorry, not controller. This is the counter. And it's a 16-bit counter. This is my 16-bit counter. And I already said 16 bits means 2 to the power of 16. That's the unit. That's a unique value for microcontroller. If you have a 16 bits, we represent it with 2 to the power of 16. If you have 8 bits, we represent it with 2 to the power of 8. And we call it unique value for the microcontroller. And what is that? It simply means that unique value is showing how many addresses this microcontroller can hold, how much memory, right? All of this is a factor of this unique number, right, for the microcontroller. So for this one, if I calculate it, I did it one more time. Again, the number is going to 2 to the power of 16 is 65,536. Remember, this is this one, okay? Do not think where I generated this one, just 2 to the power of 16. And then I've got the time. Time is 0.5. And then this one again is going to give me 32,768. So this is the same. And now, if you want, for the next example, if you want to generate with time, how do I calculate with time? Let me quickly add this one and then you are good to go. Now bus is 4, means I have main bus again, I have the time, I have all of those. All I need to add to toggle each 5 millisecond, for this one is asking to toggle each, 10 millisecond. I have to say 10 millisecond means 2 times 5. Why I say 2 times 5? Because I'm generating a square wave. T is generally 10 millisecond, but I need to consider 2.5. 2.5 means like this. Because this is a square, it was a square wave. For a square wave means 5 millisecond is high, and then another 5 millisecond is low. That's why I say instead of this, I can say even like this, 5 high, 5 low, right? Now, in order to do so, I have to say 5 millisecond over 5.5 microsecond. I already calculated how 5.5. So all I have to say, 5 millisecond over 0.5 microsecond, it becomes almost 10,000. Means it takes 10,000 count to toggle each 5 millisecond from the high to low, to move from high to low. Make sense? So that's it. We can just stop this one right in here. The remaining again is what we discussed during the lab time. In case you want to review again, you are more than welcome to review my explanation and my solution to this on Avenue.